Chapter 9, Part 1, Linear Momentum and Collision. So let me give you a little bit of an introduction of what we are going to have in this chapter. So in many situations, and I mean many situations in physics, such as, a bullet hitting another object, let's say a carrot, or, two objects hitting one another and, they get deformed. Some of the mass is removed from one object and being attached to another object. We cannot use Newton's second law to solve problems because we know very little about the complicated interactions involved in this type of situations. Okay, so in this chapter, we will introduce momentum and impulse and the conservation of momentum to solve such problems. So momentum is inertia in motion. Okay, so it is very important because that's the very small definition of it, or the shortest definition, but it's very important. So in other words, it represents how hard it is to stop a moving object. For example, a large truck has more momentum than a small car with the same velocity, okay? So even though the velocity of them is the same, but since their masses are different, okay, then their momentum are different. So in other words, the momentum is the product of mass and velocity. Okay, so P equals mass times velocity, or mv, right? V is a vector, so it is multiplied by a positive number. So P, or momentum, is a vector then, okay? So it needs both magnitude and direction. Now, V is in meters per second. M is in kilogram, okay? So the unit for momentum is kilogram times meters per second, okay? So that's the unit for momentum. So let's compare two objects. We have how do the momenta of a 2,000 kilogram car, so M of a car is 2,000 kilograms, and a 3,000 kilogram truck, so M of a truck is 3,000 kilograms. Compare if each is traveling at 30 kilometers per hour. So the velocity of each is 30 kilometers per hour. So we wanted to compare, first of all, so that's why I am not changing this unit to meters per second. I am keeping it as it is, kilometers per hour. Okay, if you remember, the P, or the momentum, was m times v, or velocity. It's a vector because v is a vector. So v in our case for these two objects are the same, 30 kilometers per hour. Whichever one that has a higher or bigger mass will have a higher momentum. So in other words, truck here with a 3,000 kilogram would have a higher or larger momentum. Okay, so that's the answer to that question. Well, let's do another comparison. So now suppose that you have the same car with 2,000 kilograms and the same truck with 3,000 kilograms for their masses. Okay, the car traveling at v of c of 50 kilometers per hour. Again, I am doing a comparison. Kilometers per hour is not a SI unit, so you have to change it if you're dealing with a non-comparison problems. But here we want to compare, so that's why I'm not transferring, or I'm not changing kilometers per hour to meters per second. So in real situation, if you're solving a problem, kilometers per hour should be, in fact, changed to meters per second, SI units, right? But I'm doing a comparison, so it's not really that important at this point. So, P is, for the car, is m of the car times the velocity of the car, and these are vectors. So m is the mass, which is 2,000, and the velocity is 50, okay? So I have these two numbers being multiplied to one another, and then this will give me 100,000 kilometers per hour, And for the truck, which is traveling with 20 kilometers per hour, so the P of the truck is mass of the truck times the velocity of the truck, and these are vectors. We have 3,000 kilograms times 20 kilometers per hour. This will give us 2 times 3 is 6. 1, 2, 3, 4 zeros in front of it. Kilograms, kilometers per hour. So in this case, the car would have a higher momentum. And the reason is very obvious because the number is 100,000 and this is 60,000. So P of C is greater than P of truck. Okay? Momentum and Newton's second law. And I really like this part of physics, this classical part of, part 1, chapter 9. The reason is that we have a very simple formula here, but it can solve many, many problems for us. Let's take a look. So we remember the Newton's second law was total F, or total force applied to an object, is equals to its mass times acceleration. So in other words, we have F of total, or F of net, or sigma F being equals to M times A, or mass times acceleration. Okay, now I can write this A, and by the way, this is also a vector. Acceleration is a vector. It needs both a quantity associated with it and a direction associated with it. It's been multiplied by a positive number as mass of the object. Remember, mass of object cannot be a negative number. So thus that we have a total force being a vector. So it needs both magnitude and direction. So I can write this as this. I can write M. For A, I can write delta V over delta T. Okay, that's a definition of acceleration, or average acceleration, right? So I can write it like this. I can write it M. Delta V is V2 minus V1, or V final minus V initial. I'm going to keep delta T as it is, delta T, okay? Now, I am going to multiply this M to this, whatever I have inside this parentheses. In other words, I can write F total like that. M V2, which is a vector, minus M V1, which is a vector, times delta T, over delta T. So I have P2, because mv2 is p, right? M times v, mass times velocity, is momentum. So mv2 is p2, and mv1 is p1, okay, over delta t. So I have delta p here, p2 minus p1, I have delta p over delta t, all right? So in other words, I have two different forms of Newton's second law, okay? The first form is F of total is ma, mass times acceleration. The second form is this, delta p over delta t, okay? So that's why the Newton's second law is very famous, because it can relate the change of the momentum of an object with the amount of force that it's been applied to, right? So we have two different forms of Newton's second law that you can see on the screen, each of which will solve some sort of problems for us. Impulse. So since momentum is mass times velocity, changing in momentum can occur if there is a change in mass or velocity, or maybe both. So in other words, if I have P being m times v, if this if the mass of the object changes, it gains mass as it's moving, or if the velocity of the object changes, or both of them change, these two can cause the momentum of an object to change, okay? we know if there is a velocity change, there is an acceleration, which could produce a force because F equals ma. So the greater the velocity change, the greater, so F equals ma, right? And if the A is delta V over delta T, if the velocity changes, then the acceleration change. And if the acceleration change, this will cause the force. Okay, so the greater the change in velocity, the greater the acceleration and the greater the force. However, when it comes to things like momentum, and when it comes to things like impulse, which we're going to extensively talk about in a little bit, it is also important for how long the force is being used, how long it took the force to apply to the object. Maybe you're applying 2 newtons over 5 minutes, or maybe you're applying the same amount of force over 5 seconds. So the impulse of this force is also related and proportion. It is also related and directly related to how long, or the timing of the force, or the timing of the motion. Okay, so now if you're looking at this, you are applying a force of F over a time of delta T. If you multiply these two, they will give you the impulse. Okay, so the impulse has the units of impulse, which is F times delta T. And it is a vector, by the way, because our force is a vector. It has a magnitude and direction. So impulse is also a vector. And it has the units of Newton. Delta T is in seconds. So newtons times seconds is our units for impulse. Now, have we seen F times delta T somewhere before? Have we seen F and delta T somewhere before? Let's see. F and delta T. F and delta T. Yes, we have seen it in the Newton's second law when it was written in forms of momentum or change in momentum. Okay, so in other words, you are dealing with impulse when you're writing your Newton's second law. So let's take a look. I have F being delta P over delta T. I can write this as this form. Delta P equals F times delta T. F delta T, right? And you have seen this before. F, a force being applied in a period of time, is impulse. So this is impulse. This is impulse. All right? In other words, if you find the change of momentum, so if you find the change of momentum in an object, okay, or in other words, if you find delta P, you have found the impulse of the force on an object. Okay? So if a problem is asking you what's the impulse of this force is, either you have a force and the time and you can multiply it, or you have the information about the momentum and you can see how much is the change of the momentum. Either way, this will be equal to the impulse. Okay, so let's review one more time. F is delta P over delta T, and we got this from F equals ma. Okay, and if you multiply F and delta T, which is here delta P, this will be the impulse. So when a constant net force acts on an object, the impulse of this force is equal to the change of the momentum of the object. And this is also very important, so I'm going to highlight it. The impulse of this force is equal to the change in the momentum of the object. So let's take a look at this, this little example. I have a ball mass of 0.4 kilograms. So the mass is 0.4 kilograms. All right. And initially moving to the left at 30 meters per second. So I have the initial velocity, or V1, of negative 30 meters per second. This negative has a meaning associated with it. It means it's going to the left. So the positive is to the right, the negative is to the left. That's why we are showing this negative, or we're using this negative to show the direction. Remember, the velocity is a vector, so it needs some sort of direction associated with it. Now I have this negative sign over there. After hitting the wall, the ball is moving to the right. Now it has the same mass, obviously, the mass doesn't change, but it's going to the right with a different velocity this time, with a 20 meters per second. So I have V2 of 20 meters per second. What's the impulse of the net force on the ball during this collision with the wall? Now we're looking for impulse. All right, so that's what we are looking for. Okay, so I know the impulse is F times delta t. F is a vector, okay, delta t is a scalar quantity, and I have it equal to change of the momentum of the object. So in other words, if I want to find the impulse, I can just easily go and find the momentum. So I can write this as delta p being p2 minus p1, okay? And p2 is mv2. Remember, these are all vectors, so I need to have a arrow on top. So mv1. I can factor out m, and I have m v2 minus v1. Okay, so delta p is m, which is 0.4, v2, 20 meters per second, minus v1, which is negative 30. This is the part that's a little bit tricky. You have to have negative 30 here. The direction is important when it comes to momentum. Okay, so you have 0.4 times 20 minus 30, or 20 plus 30 is 50. Okay, so you have 0.4, I can write it as 4 over 10, right? 0.4 is 4 over 10, times 50. All right, this is equal to 20. And it's impulse, so it has a mass of, or it is change of the momentum, so it has units of momentum. And we remember what the unit of momentum was: kilogram times meters per second. Okay, so this is the change of the momentum. So, and thus this is important, and this is equal to the impulse of the object. So impulse is momentum. One more time, example. Suppose you need to move a stalled vehicle off the road. If you give a car a shove, what happens? So it will start to move a little bit, right? A little bit maybe. What if you shove a car for a period of a few seconds? So you're applying a little bit of more force, right? The longer you push, the faster the car goes. This is impulse. This is the definition of impulse, all right? So in other words, if you have an object sitting at rest, and you are applying a force of F, of a constant F of 200 newtons to this object, okay? You applying the force for the first time over the time delta t of, let's say, 2 seconds, and then you apply the same force for the second time for 10 seconds. The impulse of these forces are different. All right, so that's the definition. That's why I told you at the beginning of this video that it is important to have, or it is important to know the time, or how long it will take for the object. So in other words, if I can find where it was, right here, how long the force acts on is also as a factor. Okay, if you're applying the same force for 2 seconds, it's different. If you're applying it for 10 seconds, it will be something else. The impulse would be different. So let me give you a thought question here. Which would you rather hit? Assuming your hand has the same initial velocity in each case, a break wall or a wall with foam on it. Okay, think about it. Obviously, all of you will say that wall with a foam on it, and that's the correct answer. I mean, I would rather to hit a wall with a foam on it rather than a break wall, right? And let's see why the reason is. We'll get back to this shortly, okay? We'll get back to this thought question in a little bit. But have that in mind, all right? Have this, you are hitting or you're punching a break wall or a wall with a foam on it. So have that in mind. We'll get back to this. So the longer the time period over which the momentum is increased, the greater the impulse, right? So for example, cannons with long barrels are used to shoot cannonballs with a greater velocity. So follow through on the swing of a golf or a baseball. These are the examples, right? So the longer, one more time, the longer the time period over which the force is applied, okay, the momentum is increased, the greater the impulse will be. Okay, so one more time, the longer the time period over which the momentum is increased, the greater the impulse. Okay, so let's talk about a long time interval. For example, stopping an object. A force felt by an object is smaller if it's carried out over a longer period of time. Okay, the impulse is the same to stop something whether it is carried out over a long time with a small force, or over a short time with a great force. For example, airbags. So the impulse is constant, okay, because eventually you will stop. But since the airbag applies force over a longer time intervals than, let's say, the windshield, so the force felt by the person is less. If I go back to this thought question, as I said, it will go back here. So the force is being applied and the impulse is the same, okay? But the time intervals are different. Okay, you are stopping your hand in a matter of few seconds when you're hitting a foam with a wall with a foam on it, versus if you're hitting a break wall, it will be less than a second. So you're feeling more impulse in this case. So the force is the same. Force is the same. This is the constant. All right. Now this delta t is different. Delta t, if it's high, then the impulse would be different versus when it's close to 0. Okay, we'll get back to this one more time later. So impulse is constant. If you want to have a large impact force on something, you want to stop it in a very short period of time. Remember the break wall, okay? This is why boxers use short, quick punches rather than a long punch. Remember the break wall and the wall with a foam on it, okay? So another example is, for example, breaking boards in karate, right? So you are applying a force over a short time rather than the long punches, all right? So crash test dummies. You are testing a new car using a crash test dummies. Consider two ways to slow a car from a 90 kilometers per hour, which is 56 miles per hour, to a complete 100% stop, meaning a zero velocity. One, or the first method of using, is you let the car slam into a wall, bringing to a sudden stop. Two, you let the car blow into a giant tub of gelatin, all right? So that it comes to a gradual halt or a gradually stop. So it will take a much longer time rather than a sudden stop. A sudden stop means that the delta t here is very close to zero in a matter of maybe 1 second. In which case there is a greater impulse on the net force of the car. So in case one, case two, or the impulse is the same in both cases, not enough information given. We're looking for the comparison of impulse, right? So we know the impulse is F times delta t, which is delta p. F times delta t, which is delta p, or change in momentum. So in other words, you will eventually end up at a velocity of zero in our case, or the dummies in the car will eventually end up in a velocity of zero. One in a very short period of time, which is case one, and the case two in a much longer period of time, okay? But they will eventually stop, so the delta p would be the same, okay? The delta p, which is p2 minus p1, okay, would be the same for both cases, same for both, okay? Because p2 is zero, it will stop, right? And p1 has a value to it, whatever it is, right? But, so the impulse is the same. The impulse is the same in both cases, but one is in a very short period of time, very, very small. So a force felt by those dummies in the car would be the same, it would be very high. The other scenario, the second case scenario, we have a much longer time, but the force will be less. Okay, the impulse would be the same no matter what. So let's talk about rain. So rain comes down with a velocity of negative 15 meters per second. Negative means it's downward to the, so positive is up, okay, negative is down, right? And it hits the roof of a car. The mass of rain per second that it strikes the roof of a car is 0.06 kilogram per second. Okay, so in each second, we'll have 0.6 kilogram of mass of a rain hitting the roof of the car. Assuming that rain comes to rest upon striking the car, so the final velocity is zero, as you can see here stated. Find the average force exerted by the rain on the roof. So the average force, or F, right, comes from m times acceleration. We obviously have no idea what the acceleration is, okay? So we wanted to solve it with this method of F being delta P over delta T, okay? So delta P is P2 minus P1. They are both vectors, and delta T is just delta T, right? So F is mv2 minus mv1 over delta T. I'm going to factor out m here, Okay, so I have m v2 minus v1 over delta t. Okay, so F is m over delta t v2 minus v1. Now, if you're looking at this, this is in kilograms, this is in seconds, and these are meters per second. But it is given to us. It says the car, it's 0.060 kilograms per second hitting car. Okay, so this value for F, we have 0.0060 for m over delta t. That's the value for it. It will stop when it hits the car. So the final velocity is 0, second velocity is 0, negative, minus initial velocity is negative 15 meters per second, isn't it? Should be 15 if I'm not mistaken. Negative 15 meters per second. So I have 0.06. Negative 15 is positive 15. Okay. And let's see, 6 over 100 times 15. This will give us 90, correct, over 100, or 0.9 Newton. Of force. So this would be that. Now, when you are, so in each second, the average force is 0.9 or 0.9 newtons being applied from the rain to the roof of the car. So let's take a look at this question. Instead of rain, suppose you have hail. Okay, and suppose hail is falling. Unlike rain, hail usually bounces off the roof of a car. Okay, so it's not going to stick. It's not going to end up being with a velocity, a final velocity of 0. Hail would bounce back. So if hail fell instead of rain, would the force be smaller, equal, or greater than the one that you calculated in lecture question 5, or this one? Would it be smaller, equal, or greater? Okay. In this case, let's write the same thing that we did. And we'll just give a final velocity of some number to see to do the comparison. Let's say the final velocity is, let's say, positive 10 meters per second. Initially it was negative 15 meters per second. And let's keep the same rate of falling of 0.06 kilograms per second. Okay, so if that's the case, then what I would have is that F is m v2 minus v1 over delta t, just like the same problem that we had in the last slide. And then this quantity is given. This quantity is 0.06 kilograms per second. Let's say the same rain just turned to be hail, okay? So I have F being 0.06, okay, times V2, which is in our case just a dummy number, like it doesn't have to be accurate. I'm just giving it a number to kind of compare. So I have plus 10, negative 15. So I would end up having a F equals to 0.06, 10 negative 15, or 10 plus 15. 0.06, 10 plus 15 is 25. okay? So you would end up having 6 over 125. This will be 150 over 100, which is 1.5 newtons. Okay, so I just gave it a number to compare. I didn't give it 0. I just gave it, 10 meters per second for a second velocity. And obviously, compared to the previous problem, 1.5 is greater than 0.9, okay? Which means that hail will apply more force because it will bounce back. It will be in a much shorter time, in other words. The impulse is the same if it comes to 0, but it's bouncing back. So it has some sort of a velocity associated with it. It's not the velocity of 0. It's not going to stop. It'll bounce back with maybe a less velocity, just like what I had here, 10 meters per second. But it will bounce back with a velocity, and it will apply more force because of that. Okay, so that's why it's doing more damage to your car. Okay, so talk about internal and external forces, and this would be the last slide for this part of the video, part 1. So internal forces are forces that objects within the system exert to one another. Okay, just like what we had before. Remember that we had a couple of boxes, and based on Newton's second law, or Newton's third law, I have box 1, box 2, box 3. So this would be the force from 1 to 2, and this would be the force from 2 to 3. I would have a force from 2 to 1 and a force from 3 to 2. But these are all internal forces. The force that's been applied from box 2 to box 3. Okay, these are pairs, action reactions, and they will always cancel out. So internal forces are the object within the system except one another. External forces are the forces that being applied to a system from an outside agent, okay, from an outside source, and this can cause the change of the momentum. So this can cause the change in momentum. Okay, end of part 1 of chapter 9. We'll continue shortly with part 2.